Hello. In our last video, we talked about the quick approximation method. And the idea here is to use 0.0001 instead of using 0 to find out what's going on at that instantaneous moment. Well, there are other ways to do this as well, because really we're trying to find out 0, not 0.0001. So I can do this in the calculator, which I'll show you first, but to really appreciate that, you can do it through algebra, and that's what this video is about. So to show you the calculator first, we're going to go back to this equation where someone was throwing a baseball up and the baseball fell down. And this is time and height. So I'll go to my calculator, go to y equals, type in 100x minus 16x squared. Now the first one will tell me, you tell me the time and I'll tell you the height of the ball. But if I want to find the derivative, the instantaneous rate of change, in y2, I'm going to push math number 8 for derivative. And we want to take the derivative of y1. So to do that, we push vars to the right for y vars, number 1 for function, choose y1, comma x, comma x. Now the reason for the x's is it's in terms of x with respect to x, and we're referring to y1. So we go to our table set, second window, make sure that the independent is on ask and your dependent's on auto. Then when I go to the table, my input is time, y1 is the height, and y2 is the instantaneous rate of change. It is the feet per second rate of change. So when I type in 0, at time 0, the ball is 0 feet off the ground, but is traveling 100 feet per second. 1 second, the ball is now 84 feet in the air and is traveling 68 feet per second. 2 seconds, the ball is now 136 feet in the air, traveling 36 feet per second. At 3 seconds, the ball is 156 feet in the air, traveling 4 feet per second. Notice it's slowing down as it reaches its apex. At 4 seconds, the negative means it's traveling downward at 28 feet per second. At 5, 60 feet per second. At 6, now the ball is 24 feet in the air, going 92 feet per second downward. And you can kind of see what's going on. But again, the calculator is doing the work. The calculator is finding out what happens at time 0. So we need to do this by algebra. So that's what this video is all about. So when I go to, and all the steps on how to do the calculator are here in the notes. There's one to practice. But the idea is, how can I use the definition of the derivative, which is right here, to find the derivative? You take the limit as h approaches 0. Remember, plugging in 0 would be undefined, of f of a plus h minus f of a, a formula we discussed in the beginning. So if I have a function of x squared, how can I find the derivative at 3? Well, let's start working on the algebra before we start plugging in any numbers at all. So we have the function x squared, and I want to find the derivative function. Like in the example we just did, the original function can tell me if give me the seconds, give me the height of the ball. The derivative can tell me the rate of change, the velocity of the ball, let's say, in an example. So I'm going to walk through the algebra, but you really need to practice this. So basically, to find the derivative function, we take the limit as h approaches 0. We're going to take x plus h minus f of x over h. Now remember, I cannot plug in 0 for h because then it would be undefined. So using some algebra, we'll get to a point that we can. So basically, f of x plus h means we're going to take x plus h and plug it into the function. So instead of x, we put x plus h. That's why it's x plus h squared minus the original function over h. And when I start cleaning this up, x plus h times x plus h simplifies to x squared plus 2xh plus h squared minus x squared. We notice it starts simplifying. The x squares cross out. I can pull out an h, I can factor out an h, and then the h's cross out, because h divided by h is 1. Every time I'm writing limit as h approaches 0 because I cannot plug in 0. But once this starts simplifying, we end up with the derivative function will be the limit as h approaches 0, 2x plus h. Now I can plug in 0 for h. Notice it disappears. Plug in 0 for h, and the derivative function would be 2x. Okay, let's do this again. Let's say the function was 2x squared minus x. Okay, going through the same process. There's our definition of the derivative. I'm going to take x plus h and plug it in everywhere there's an x. So instead of x squared, I put x plus h squared. So it'd be 2 parenthesis x plus h squared minus, instead of x, I plug in x plus h, minus the original function over h. Again, we're trying to plug in 0 for h. We take x plus h squared, simplify, distribute the 2, distribute the negative subtraction, distribute the subtraction, algebra. And when we get to this step, we still have limit as h approaches 0, but you'll notice it starts simplifying. 2x squared minus 2x squared, x minus plus turns into 0. Factor out an h over h is 1. And then we get to this point when now I can plug in 0 in for h. Limit as h approaches 0, plug in 0 for h. That becomes 0. You're left with 4x minus 1. There's your derivative function. So if I plug into the original, I would use this one. To find the rate of change, I would use this one. Okay, so going back to that other example we talked about with a person throwing the ball in the air, if we did the same process where instead of x plus h we'll plug in t for time plus h, our function is 100t minus 16t squared. Everywhere there's a t, I plug in t plus h. That's here. Minus the original function. Again, this would be distribute, write it twice and distribute becomes this. Distribute the subtraction, distribute the negative 16. You get to this point. And again, every time we're writing limit as h approaches 0 because I can't plug in 0 yet, it starts simplifying. 100t minus 100t minus subtraction t squared plus 16t squared. At this point, we're left with this. We pull out or factor out the h. And then we finally can plug in 0 for h. And we find the derivative function of 100 minus 32t. Again, here's the original function. Here's the derivative function. Now, to kind of prove that, I'm going to go back to my calculator, go to y equals, and in y3, I'm going to put 100 minus 32x. Now, this is the calculator doing the derivative. This is our derivative function. When I go to the table, you'll notice that y2 and y3 have the same values. You found, using algebra, the derivative function instead of just using the calculator. You get the same values. So that's where we get that 2 seconds from. Okay? A couple things to note here is that there's a few places where you cannot take the derivative. For example, a sharp corner and an asymptote. It's unable to find a derivative. Then I'll teach you the shortcut in the next video.